While I'm at it, I thought I would just give you a little bit more of a specific rundown on this week's exam, this Monday's exam. Uh, Definitely, this homework, week 10 and 11 homework, is essentially the material for the whole exam. Now, there's not a question related to every one of these things because you kind of have to know the Pauli exclusion principle to do anything else. So it's not like I'm going to ask you a specific question about every item in this list. But you definitely need to know these, how to explain these trends using energy level diagrams. That's probably 30% of the test. So 30 points out of 100 are dedicated to looking at the evidence for our claims that fully filled subshells are stable, or that noble gases are hard to ionize and alkali metals are easy to ionize, and half-filled shells are stable. So pay particular attention to number 18. You'll need to know definitely how to come up with term symbols. You do not need to know the P3 system. If I can test you on a 2-electron set of term symbols, then I'm confident you could figure out a 3-electron. A 3-electron system would just take too long, and you'd spend the whole hour doing just that one problem. But you need to be pretty quick and pretty competent on doing a 2-electron configuration. And then this last piece we really didn't talk about in class because it's pretty simple, but that doesn't mean that you'll pick it up if you've never really talked about it. So I'd like to show you this series of character tables. And you drew the d orbitals and the p orbitals as a part of this week's homework. And I just wanted to talk about the character tables. And you'll notice that in these particular situations, we have the z, x, and y. That would be your p orbitals, px, py, and pz. So in a system of C2H, your pz orbital is going to have the symmetry of AU. Your px and py orbitals are going to have BU symmetry. What about the z orbitals? Well, you have the d orbitals. You have the dxy orbitals, and that orbital, and that would be Ag. You have the dxz, and you have the dyz. And those two orbitals would be Bg. What about the 2z squared minus x squared minus y squared? That's going to be a top row almost always. You find a z squared here. So when you find that z squared, that's that dz squared orbital. So here it's A1. Here that orbital's A. Here that orbital's A1. Here it's A1. Okay, down here A1. Here it's AG. Okay, and then you have the x squared minus y squared orbital. Here it's BG. Okay, so you have an easy time if you just know where to look on finding the Millikan symmetry for the different d orbitals and for the p orbitals. So the px orbital is wherever you find x. The pz orbital is wherever you find z. And so it's pretty easy to find where those orbitals show up in their symmetry in particular crystal fields. Now, what do I mean by a crystal field? Well, it would be an atom surrounded by nearest neighbors. And so if I had a situation of an atom in the center of a square planar structure, then that atom is in a crystal field with 4 nearest neighbors. There's an atom here, an atom there, an atom there, and an atom there. And so that would be a D4H if this was a square. In this particular case, I've drawn a rectangle, so that would be a D2H system. And so in that D2H system, my dz squared orbital would be Ag, my xz and yz would be Bg, and the px, py, and pz orbitals would have these symmetries. Then I could use multiplications of these to determine if light was going to allow a transition from this particular z orbital to that p orbital or vice versa. One thing I haven't talked about is s orbitals. S orbitals are fully symmetric. So what do you think fully symmetric means? It means top row. So the s orbitals are always going to be top row. So in all of these character tables, an s orbital would be top row. So that's a little bit of information on that last part of the homework, where we talked about the Millikan symmetry representations of sp and d orbitals. And these different octahedral fields, it's just going to be, these different crystal fields are just going to use whatever character table that matches the field type. It's an octahedral, it would have 6 nearest neighbors. If it was a tetrahedral, it would have 4 nearest neighbors in a tetrahedral arrangement. C4V might be an octahedral with one long bond, and so that breaks the octahedral symmetry and gives you a C4V crystal field and a C4V character table. And then you can look at the selection rules. So take all of those different symmetries and do the direct products to see if the direct products with light would be allowed by symmetry. So that's a rundown on the specifics for this week's exam. There will be a couple of problems related to the propagation of uncertainty, very similar to these here on week 9. Basically looking at RSD calculations and also reporting data, making sure that the place value for your uncertainty matches the place value in your mean that you're reporting. So hopefully that'll help you guys be successful.